Calculus video 74, U substitution. So U substitution, this is going to be a very important concept for us in calculus. We will use it constantly in Calc 2, in physics, and honestly the rest of calculus here. First I'll say that there's no magic about the letter U. We could easily say W substitution or V substitution or cloud substitution. We just tend to use U's. So we call it U substitution. The goal here is to use U substitution to make a difficult integral easier to integrate. We're going to take something that looks kind of complex, and by letting U equal a portion of whatever we're trying to integrate, turn it into something that we can integrate easily, that we know how to integrate. You can use U substitution with both indefinite or antiderivatives or definite integrals with bounds. So it works for either one. And what will happen is we'll get an example that looks something like this. Okay, so the example we have here is the integral. This is an antiderivative or indefinite integral, no bounds. And all the ones we'll have at the beginning here for these videos, the first few videos will be antiderivatives, and then we'll move into how do we do U substitution with bounds. Okay, so in this case, the integral of 6x squared times the square root of 9 minus x cubed dx. And as you can see, this is a more complicated integral. Let's first start with what not to do. You cannot simply integrate each term or each expression by itself. In other words, you cannot just integrate the 6x squared dx multiplied by the integral square root 9 minus x cubed dx. It doesn't work. You can do that if the terms are being added, but not if they're being multiplied or divided. So don't do that. What we're trying to undo here is a chain rule. I should have written that up there. I'm going to scroll back up here. Goal, use U substitution. U substitution helps us undo, if you will, a chain rule. So you're thinking of it, if I was to have a function that I took the derivative of, and I needed to use the chain rule to take the derivative, if I were to go back to the original function, I would need U substitution to help me undo that chain rule derivative that I just took. Okay, it's undoing a chain rule. It might look down here like we're kind of undoing a product rule, but this is really undoing a chain rule here. One of the main parts about a U substitution is you recognize that you have an integral that looks pretty complicated. I don't know how to just get an answer here. So that might tip you off that I need to use U substitution here. And the other part is choosing the U value, the expression that you're letting U equal correctly. You want to choose U correctly. In this case, we're going to let U equal 9 minus x cubed. And the reason I'm letting U equal 9 minus x cubed, and one thing I often think about is, I want to let U equal something whose derivative is also in the problem. Now, that doesn't work every time, but about 90% of the time, this is what I'm thinking. Let U equal an expression whose derivative is in the problem. Well, what is the derivative of 9 minus x cubed? That would be negative 3x squared. And you might say, well, negative 3x squared is not in the problem. And I'll say, okay, not exactly, but I have 6x squared. And we can deal with the coefficients. The fact that it's 6x squared and not negative 3x squared, we can deal with the 6 and the negative 3. But the x squared is what I'm looking for there. Okay, so having U equal 9 minus x cubed, whose derivative is negative 3x squared, knowing that there's an x squared in my problem elsewhere, tells me I'm on the right track. Also, a good portion of the time, the thing you want to let u equal is like inside of a parentheses, if you will. In this case, it looks like it's inside of a square root, but a square root, the 9 minus x cubed, is inside of a square root, but a square root can be thought of as like 9 minus x cubed to the 1/2 power. Right, we could think of this as 9 minus x cubed to the 1/2 power, and a 6x squared out here that I'm integrating, dx. And oftentimes, the u value is whatever is inside that parentheses. Inside the square root, inside something being raised to the 3rd power, inside something being raised to the 2/3 power, right? That's a lot of times what's happening. Okay, so we're going to let u equal 9 minus x cubed. So what we have at the very beginning is, some people call this is like x world. I'm integrating a function with respect to a function of x's, 6x squared, square root of 9 minus x cubed, dx, right? So this is sorry, the word just skipped me. This is in the differential form. Sorry about that. This is in differential form, right? You should be thinking, if I had y as some function of x, differential form says that I have dy is equal to the derivative of that function dx. And then the antiderivative says that if I take the integral of dy, that's going to give me my y, is equal to the integral of f prime of x dx. That's where this form is coming. This is the integral of some f prime of x dx. That 6x squared square root of 9 minus x cubed is the f prime of x. So we're going to integrate that, or what we often think about here is this is the antiderivative of this function with respect to x. We kind of think about this dx as kind of like with respect to x. So I am in this sort of x world here, where I have functions of x and dx. If I'm going to do a u substitution, I have to turn everything into u's. So I need my functions to all be in terms of u that I'm integrating, and instead of dx, I need du. I need to do the antiderivative of the u function with respect to u. So I need to be able to change not just the 6x squared square root of 9 minus x cubed, all of that into u's. I also need to change the dx into a du. Here's what you do to do that. We're going to use that differential form again. When I have u is equal to 9 minus x cubed, I'm going to take the derivative of both sides, but in differential form. So the derivative of u, we're going to write that as du is equal to f prime. So the derivative of 9 minus x cubed is negative 3x squared, and then dx. And what that does is allows us to solve for dx. We can solve for dx and then replace it. So I like to solve for dx. So to solve for dx, I'm going to divide both sides by negative 3x squared. And I don't know why, but I always like to write my dx over here instead. So dx is equal to du divided by negative 3x squared. So I'm going to replace this dx up here with whatever it's equal to, du divided by negative 3x squared. I'm going to replace the 9 minus x cubed here with just u. And I'm going to leave the 6x squared for now, with the hope that the x squared in the 6x squared cancels out with whatever I have when I'm replacing my dx here with du divided by negative 3x squared. Okay, it looks something like this. Let u equal 9 minus x cubed, du is negative 3x squared dx. Dx is equal to du over negative 3x squared. You should be writing this part every time. You do want to write down all three of those things. So the integral of 6x squared square root of 9 minus x cubed dx becomes the integral of 6x squared. That part did not change. But the square root of 9 minus x cubed, I'm going to write that as the square root of u, since u is equal to 9 minus x cubed. And then dx, I'm going to write that as du over negative 3x squared. coming from right here. dx is equal to du over negative 3x squared. And what I'm hoping for is that the x squareds cancel, which they do. I have x squared here, canceling with an x squared in the denominator. Now the reason I don't have to worry about 9 minus x cubed having the exact 6x squared derivative is these are just coefficients, and we can work with those. We have 6 divided by negative 3. 6 divided by negative 3 is negative 2. And in fact, I can take that negative 2 and bring that out in front of the integral sign. So I have negative 2 from the 6 divided by negative 3, square root of, square root of u, let's write that as u to the 1/2 du. Negative 2 integral u to the 1/2 du. Okay, let's pause for a minute. Using u substitution, what we've done is we've taken this complicated integral, the integral of 6x squared, square root of 9 minus x cubed dx. That looks pretty complicated. And we have turned that in to this sort of simple-looking antiderivative. Negative 2 integral u to the 1/2 du. We can do that. So we do. This is equal to negative 2 times the antiderivative. I'll do u to the 3/2 divided by 3/2. That's the same as multiplying by 2/3. We're doing the antiderivative without bounds here, so we need the plus c. That will be negative 4/3, 2 times the 2/3, u to the 3/2 plus c. But please don't stop here. The original function was in terms of x. We would like our answer in terms of x as well. So we're going to go back to this u is equal to 9 minus x cubed, and we call it back substitution. Instead of letting 9 minus x cubed equal u, we're going to go back and let u equal 9 minus x cubed for a final answer of negative 4/3 times 9 minus x cubed to the 3/2 plus c. And we have taken the antiderivative of a pretty complicated function. The great thing about antiderivatives, you can check your answer. So, we won't do this every time, but for the first time, let's check it just to be sure. What this is the derivative of this negative 4/3, 9 minus x cubed to the 3/2 plus c, should equal our original function up here, 6x squared, square root of 9 minus x cubed. Let's see if it does. The derivative says I'll take power rule here. I'll bring the 3/2 down, so that's negative 4/3 times 3/2. 9 minus x cubed, subtracting 1 from the exponent would be 1/2. And then chain rule says I need to multiply that by the derivative of the inside, the derivative of 9 minus x cubed, negative 3x squared. Okay, I see here that the 3 here and the 3 here cancel. Negative 4 divided by 2 is negative 2. Negative 2 times negative 3 is positive 6. I also have the x squared. And the 1/2 power is a square root 9 minus x cubed, which is exactly what we started with. So yeah, this was the correct antiderivative. That is the idea of u substitution. Take a complicated problem, let u equal one of the expressions. A lot of times that the derivative of what we're letting u equal should be in the problem, at least, multiplied by some sort of factor, some sort of constant there, like ours was here. Rewrite it, plug in the u, solve for dx, so that you can replace dx with du, usually du over something, but whatever it happens to be. Make sure everything is now in terms of u. We would call this right here like u world, because I've got a u function and I've got a du, as opposed to x's and dx's. One thing to note, we could not have done the integral at this point here. Before we canceled out the x squareds, you can't integrate, at least not yet, you can't integrate when you have both x's and u's. We either need to have all x's and a dx or all u's and a du. Okay, good. Let's try one more. So again, let's use u substitution. we'll have some sort of a complicated integral here. Maybe the integral of, let's see, (8x) over 3x squared plus 5. All right. So the question is, that looks like a pretty complicated antiderivative. Again, this is not equal to. Please don't do this. You cannot simply take the integral of 8x dx and divide that by the integral of 3x squared plus 5 dx. It does not work. Don't do it. Instead, we need to do a u substitution, and we're going to let u equal one of the expressions here, with the hope that the derivative of that expression is also in the problem. Again, 90-something% of the time, that's what we're looking for. So this time, let's let u equal, what do you think? I think 3x squared plus 5. I think 3x squared plus 5. Because the derivative of that is 6x dx. And I have an 8x in my original problem. I'm getting a derivative of 6x dx. Therefore, those x's will probably cancel. And so I'm going to solve for the dx here. Dx, dividing both sides by 6x, I get dx is du over 6x. And so I'm going to take this u equal 3x squared plus 5. I'm going to replace 3x squared plus 5 with u. And I'm going to take this dx equals du over 6x and replace that dx with du over 6x. Should look something like this. The integral of, I'm going to leave the 8x for now, divided by 3x squared plus 5, that's just going to become u. And dx becomes du over 6x. Okay, I have x's and u's here. I don't like that, but thankfully, x here cancels with my x here. The fact that I have 8 over 6, that's not a big deal. 8 over 6, that's 4 over 3. We'll just bring that right in front of the integral. So we get equals 4 over 3 integral of 1 over u du. Okay, let's take the antiderivative there. That would be 4/3 times the natural log of the absolute value of u plus c. But don't stop here. Let's go ahead and replace the u with what it was, which was 3x squared plus 5. And we get a final answer here of 4/3 natural log absolute value 3x squared plus 5 plus c. And one more thing here. If you had this answer for me personally, that would be correct. But you should notice that no matter what x value you plug in here, if you square that x value, even if it starts off negative, if you square it, it's positive, times 3 plus 5 must be positive. So for all x's, 3x squared plus 5 is already positive, so the absolute values are redundant and not needed. And we could write this as 4/3 natural log 3x squared plus 5 without the absolute values, because it can't be negative anyway. Very good. And one more thing, just for fun, I really like the integral of 1 over u du, because we get the natural log of the absolute value of u, and the natural log of the absolute value of u is the same if you look at it upside down. Turn your screen upside down if possible, turn your head upside down, and you will see it is still the natural log of the absolute value of u, and I find that quite fascinating. Okay, that is a couple of examples of u substitution. There's more to it than that. There's a little bit of nuance and some different kind of problems to work through. I'll stop this video and do a few more examples in the next.